great.
Okay.
So this is recorded, so everybody else, if you can, mute yourself, then the recording will be better. The sound will be better. Yeah. Thank
Yeah,
you.
and Pencheng, instead of waving, maybe say something, because I'll
Okay.
put
Okay.
you
Well,
I'll put the small icons, so
okay. Okay. What
if you
do?
don't speak, you won't show up.
Okay. What do?
Like, I can
I'll
see
watch
your
you. Yes.
screen.
Yeah. Thank you. Yeah.
Okay, so I'll start then. So what I would like to report to you guys is some progress that we made in realistic calculations, in particular of iron selenium. So we included, I'll explain that a little better, screen Fock exchange and Hund's metal correlations in our ab initio simulations, and we got a very nice agreement with experiments of several quantities. So let me just jump directly. Okay, these are my collaborators. Tommaso Gorni, this is really the work of Tommaso Gorni mainly. So he's a postdoc in my group in ESPCI Paris, and he's really an expert in DFT and also now with slave spins, including correlation series calculations, and he's done a great work in comparing with experiments. Pablo Villararibi was a PhD student in my group until a couple of years ago, and if time allows, I'm reporting some of his work, but he's also participated to the work of Tommaso. And my collaborator Michele Casula is also here in Paris, and I guess you all know him. So we've done this work together, and it's on the archive, Struggling with PRL. So you'll see here the reference all over the talk. So I'll be talking about iron selenium. Of course, this is not a crowd that needs introduction but I'll just focus on a couple of aspects. So iron selenium, it's slightly atypical among the iron-based superconductors because it's the simplest one. And in the phase diagram, it doesn't have magnetism, but like the other ones, it has an orthorhombic distortion at low temperatures, and in which superconductivity arises. I'll focus mainly on the tetragonal high temperature phase, but then we'll also say something about the superconducting phase, and in particular, what you see here, I'll focus on the fact that the superconductivity, the TC for superconductivity almost quadruples under pressure. So the basic blocks of all the iron-based superconductors, as you know, are the same, are this buckled plane of iron on a square lattice and ligands above and below. And iron selenium has done all of that, whereas the other families has some charge reservoirs in between. The symmetry is always tetragonal or orthorhombic in most of the cases, and the itineral electrons approaches that we can use to try to model and understand these materials through DFT, for instance, give the correct Fermi surface topology. That is that of a compensated semi-metal with hole pockets in the center of the Brillouin zone and electron pockets on the sides. These pockets are formed mainly from 5 bands of main iron 3D character that disperse 4 to 5 electron volts, and with some partially lifted degeneracy that make that all of them participate to the low energy excitations, and they host 6 electrons in the parent compounds, and then one can dope. The nesting of these pockets provides a natural mechanism for the magnetic phases that one finds, and also a natural spin fluctuation mechanism for pairing, which is probably the mainstream scenario for superconductivity. However, we'll see that there are some difficulties in modeling that we'll try to face. So to tackle. So this is the ARPES of the normal phase in iron selenium in the tetragonal phase along the gamma M cut. I'm quoting this ARPES from this group, but there's been a lot of work, and of course consensus has taken some time to rise. I guess we can discuss the details of this, but I'll refer to this scheme of bands in the gamma M cuts, and in particular to the fact that XY band at gamma is sunk, and that seems to be there seems to be an erasing consensus on this, and on the other hand, all the 3T2G orbitals participate to the bands in the cutting the Fermi level at the endpoints. And I will also focus on the topology of the, on the sides of the pockets of the Fermi surface. So I will use these two schemes and refer mainly to these ARPES experiments in the following. So the main thing to be understood right away is that although DFT gives the right topology, it by no means gives the right bands. So here we're just putting any calculation that you can do. PB is GGA, but it could be LDA. Bands are way too dispersive. Even if they cut as say the topology of the Fermi surface is not wrong, but the sizes of the pockets are quite wrong in almost all iron-based superconductors, and for sure the bands are way too dispersive. And you see that you have to renormalize iron selenium by a factor maybe 5 to 6 to get something in the ballpark of what you see in the experiments. In general, the purely itinerant model has problems which are, again, this DFT bands too dispersive. In many compounds, it's 2 to 3 times. In most correlated compounds, is even more. The ordered magnetic moments are unusually overestimated by LSDA. Here are the experiments. Here are the LSDA estimates, and not always the high TC compounds have this nesting properties, and sometimes the low TC compounds do have it. So it's clear that electronic correlations should be taken into account, dynamic electronic correlations, which are missing in the purely itinerant model. And also there is a direct evidence from X-ray emission spectroscopy of local moments in the paramagnetic phase. So how do we introduce this? Well, we use a multi-orbital Hubbard model in which you have a one-body part coming from density functional theory, and an interaction that includes intra-orbital, inter-orbital interactions for both opposite and parallel spins. And the difference between the inter-orbital interactions among them and compared to the intra-orbital interaction is embodied by these parameters that is the Hund's coupling. That is a fraction of the Coulomb repulsion, the local Coulomb repulsion, and is the one that gives rise to the well-known Hund's rules in isolated atoms. Now, the fact that these Hund's rules are very relevant for conduction electrons in the localized states, it came as a surprise in the last years. And I would just want to play a little game by showing how non-trivial things are. What I'll show here are simplified model facts, but these are well known. I'm plotting the quasi-particle weight as a function of the interaction strength for several models that you can imagine. So take a certain number of independent bands in which you have only then an intra band local interaction that I call U intra. Then at some interaction strength, your quasi-particle weight will go to 0 and you'll have a multi-insulator. Now, imagine that you turn on the inter-orbital interaction. So the bands don't talk to each other than with this inter-orbital interaction, both for parallel and anti-parallel spins. Well, so you seemingly have more interaction, but on the other hand, you'll have a multi-insulator at a much higher critical interaction strength. So at the critical interaction strength where you had a multi-insulator for bands that were not interacting with each other, when they start repelling with the interband, inter-orbital mechanism, they get more metallic, and you need more interaction to get a multi-insulator. Now, imagine that you reduce, as we do with Hund's coupling, these two terms, inter-orbitals, in this way. Well, now you have U critical for the mod transition at a much smaller interaction strength. So it's really non-intuitive And this is because it's not just the balance between you and the hopping that plays. It's more complicated. It's really the degeneracy of the local ground state versus the active hopping channels that tunes the kinetic energy and then the euclidical. But okay, this is just a little scheme just to show how things are non-intuitive. And this was for half filling. Now, imagine that you go out of half filling, it's even more complicated. And in fact, even if, as we saw, the Hund's coupling generally correlates and reduces the quasi-particle weights, it also pushes away the Mott transition out of half filling, so that you actually tend to have, for the quasi-particle weight, quite long plateaus in which you have strong correlations, but far from the Mott insulator. And this gives really a ballpark to strong correlations, because you don't need to be close to a Mott insulator to have them. And that's why they're encountered so easily in many materials which are in this situation. So where Hund's coupling is at play and you are off half filling, but not too far from half filling. Now, I'm showing here some DMFT and some slave spin results just to show that they are qualitatively always in agreement and semi-quantitatively also, in particular in the 5 orbital cases. So we use both techniques, but results do not depend on which technique is used in their main features. So there is then something else that happens in realistic models. So when you have bands which are not identical, is that in these plateaus, in these long zones where you have strong correlations, but not yet Mott insulators, correlations typically get orbitally selective. So there is a lot of work that has been done in this respect, both from the Rice group, from our groups in the last 10 or more years, and these orbital selective correlations in these zones of strong correlation dominated by Hund's coupling that are nowadays called Hund's metals are ubiquitous. Here we did some calculation for iron selenium and iron tellurium long ago, but these were very similar to the calculation by Rong Yu and Chimiao Si on the 111 and many others. And you will probably have seen this phase diagram with this Y-shaped phase diagram many times, and this is very universal. So it shows that if you have small Hund's coupling, you typically, as a function of the interaction strength, you have a metal to Mott insulator transition at some U, whereas really when Hund's coupling is sizable, you go through this phase, which corresponds to this Hund's metal phase, in which you have orbital selectivity. Be it in Adela's model, a sharp orbital selective Mott transition for some orbitals and not others, or a more gradual crossover, it's always there, and for the shape of the phase diagram is always the same. It's this Y shape so the zone widens with Hund's coupling. So there was a
Lucas, do you mind if I just raise
sure.
a question for the purpose of discussion? So in my mind, there's a confusion as to what the operational definition of Hund's metal is. Because when we did these calculations, one of the things we found is that there's a precursor to the orbital selective Mott phase. And that's the precursor regime where orbital selectivity appears. But at the same time, the lower Hubbard bands and upper Hubbard bands are still there. So I'm not sure what your operational definition of Hund's metal is, I guess.
Well, for me, as you said, the operational definition is given by the similarity between these phase diagrams. So here we are in idealized models. So clearly the onset, I think this is what you call the precursor. The onset of orbital selectivity really coincides sharply with an orbital selective Mott transition. When you have a more realistic calculation, clearly, as you see in both our calculations, it turns more into an avoided orbital selective Mott transition. You get a very heavy fermionic particle, but not a clear localization that then can happen further on, but the onset of selectivity is what is universal. Here is just the simplicity of the model that makes it coincide sharply with an orbital selective mode transition.
Right.
But in that, I don't think there is no real confusion. The confusion is more in the general definition of Hund's metals, and I agree with you, but that's a vast discussion that maybe we should have.
No, we should have probably a separate time, but I think the question of whether there's a lower hover band and upper hover bands has been the source of the confusion. You know, all our calculations that they are always there. So to me,
I think for me there's no confusion. They are always there. They might be at a distance that you don't expect, because you have to renormalize also the mod excitations with J. But I don't think it's a general fact that they're not there. Of course, if you go at very low interaction strength, they might still overlap. That's a possibility, and that we saw that. But they're there.
Okay, thanks.
Okay, so I just wanted to quote a lot of work that has been done in theory with different techniques, and I think they all agree on the main facts that there is this selectivity of the correlations, both in models and in realistic calculations. It's really an outcome of the local many-body physics, and a lot of work has been done, but I think there is consensus in this respect. And also the fact that the XY orbital is always the most correlated one. It's also pretty well established. In particular, as far as iron selenium is concerned, I remember probably this Eichhorn et al. Was one of the first papers doing this with the MFT, and also of particular importance in the community played the role of these nature materials from the Rutgers group, in which there was a lot of comparison between the different materials. But I guess that in the end, the picture that comes out of this work from many groups is quite substantially in agreement on the main facts. So experiments also confirmed a lot of this physics. Now we'll go quickly through a few points. These were done for me. I mean, the correlation strength and the orbital selectivity increases with hole doping. So going from 6 towards 5 electrons in general in these calculations. And I think this is confirmed in experiments. So I'll show some results from the 1 to 2 family, which is the one that can be actually doped a lot and in a very detailed way with holes and electrons. But in here, it's one of our main comparisons experiment for the Sommerfeld coefficient, which tracks the strength of the correlations as a function of doping, and here also with some further substitution of the cations that increases the correlation in the 1 to 2 family, shoot up, whereas the DFT cannot follow. It's really flat, or more or less flat, whereas this is the outcome that you have with DFT plus slave spins. You have a very similar outcome with the MFT. And this requires no fine tuning. There's just one value of the interaction, and only the DFT is changing among these different compounds. So I think this really proves that Hund's coupling is at play, and there is a lot of physics due to correlations here, local correlations at play in these materials. And DFT is completely off. Another thing that I quote quickly is the fact that also the selectivity is increasing with hole doping, and this is the theory. This is what several estimates that we can have from experiments, and they also show a divergence of the selectivity between the different bands at the Fermi level and the different probes that are sensitive to the different bands with hole doping. So both the fact that the Hund's coupling is important and the selectivity is important, I think are very, very well confirmed by experiments. And these I will skip, but also the local moments that come out of the strong Hund's coupling are also seen in X-ray emission. Particularly for iron selenium, orbital selectivity was seen in a lot of ARPA's works. There is a nice work from still the Rutgers and group with Mingi. I think at that time she was probably in NZX Chen's group, but and there are other works. Here I quote some of the estimates of the mass enhancements for iron selenium and iron selenium tellurium, and they're very spread. So selectivity is there. And also there is a very nice work from the group of Seamus Davis with quasi-particle interference they showed that the spin fluctuation pairing can be reconciled with experiments only if one makes it orbitally selective and if one uses orbital selective differentiated coherence among the quasi-particles. So now let's go to our results. I'm showing here then again this renormalized simple DFT. And since these correlations are important as introduced from Hund's coupling and not just as a squeezing of the bands, and also they're highly non-intuitive, we did this calculation through Slay spins. And this is just to show that Slay spins on the traditional DFT are not able to reproduce in detail these bands. This is what we have. In particular, I would like to focus on the fact that here the XY band is in yellow and it's still at the Fermi level at gamma, whereas again, this is what I called your attention on before. I would like to see it sank. And these results are not very sensitive on the choice of these values. As long as we are beyond this crossover into the Hund's metal phase, you can vary this among some realistic values. You will still have the same topology of the bands, unless if you go to very unrealistic values. So we are pretty dissatisfied by this. And in fact, we try to move beyond the traditional DFT into what I will show you, hybrid functionals. Now, let me just focus also on the fact that if you look at the Fermi surfaces, the DFT Fermi surface is not cured of these problems, which are the fact that these pockets are too large compared to experiment. This is a scheme that is a little bit enhanced, but it's taken from experiments, and the experiments don't see these three pockets in gamma, and they see small, very elongated pockets at M. So what we have done is we have moved into the field of trying to understand how this Fermi pocket shrinking is done. And there's a lot of work that have been done again in the community, both evoking a dynamical mechanism, so a self-energy which is due to interband scattering, or also the fact that the DFT doesn't take into account correctly the short range interaction, for instance, through incorporating them through Artifact. And this mechanism can both have a shrinking of the Fermi surface. In particular, only the second one seems to be giving correct shrinking for iron selenium. So this is interesting for us. But in other materials like the 111, they seem both to give satisfactory shrinking. But we want to really have it ab initio to not just the topology of the Fermi surfaces, but the sides of the Fermi surface, the pockets, but the whole band structure. So what we tried is follow a path which has been already explored of going beyond LDA or GGA. So there was some nice pioneering work from Van Schilgaard Kotler with Jan Tomczak, in which they use quasi-particle self-consistent GW. Another from the group of Silke Biermann with Ambroise van Rockegem using screen exchange plus the MFT. And there is a recent also work from the George and Kotler group in analyzing the ARPES from lithium iron arsenic and establishing that DFT in the traditional LDA JJ form is not able to yield a correct description. What we want to stress is that, however, we can go beyond GGA. We do it with HSC, so the hybrid functional, and we obtain a corrected static reference Hamiltonian, so one body Hamiltonian, on which we can still include the local correlation from slave spins or the MFT and get a nice agreement in the end. So what we would like to show is that still, by doing the non-trivial decoupling of dynamical interaction, which are dependent on omega but not on k, once you have the right non-local static Hamiltonian, this yields good agreement with experiments. And indeed, So this is what we do. I can come back to the details of what is the hybrid functional, but this is one of our main results. You see that simply using, again, an interaction value, which is in the ballpark of what puts you right beyond the crossover into the Hund's metal phase. And simply using the standard parameters of the hybrid functional, we get this kind of band structure, which is in a very nice agreement with the experiments. It's not perfect, but it has indeed the sinking of the gamma band, of the XY band at gamma, has a nice shrinking and elongation of the pockets at M, and a nice match of the Fermi surfaces. And if we use this to predict whatever we can predict with this band structure, which in our technique with slave spins doesn't have the lifetime, so we can predict only things that do not depend on the lifetime, but with DMFT we are doing it, and we will be able to go beyond. One thing that can be reconciled with experiments is the specific heat Sommerfeld coefficient, so the slope of the linear part of the specific heat in temperature. This is too small compared to estimates that can be given from experiments, which are around 12 millijoule per mole Kelvin square. DFT alone, of course, gives it too small because you need renormalization, but renormalization on traditional DFT give a huge value, whereas using the fact that one band has sunk, this take away density of states at the Fermi level, and indeed HSE, so the hybrid functional plus slave spin, give a much better agreement with experiment. And then quite surprisingly, also the interband optical conductivity agrees very well with experiments. Here we are putting experiments in which we have subtracted the Drude peak, because again, the Drude peak needs the lifetime that we don't have with this technique. But okay, it was fitted by the experimentalists, and so it was easy to subtract it because we used the fit of the experimentalists to subtract the Drude peak, the narrow Drude peak, because there's typically two Drude peak used by people doing optics in fitting this data. So these experiments as what remains after subtracting the Drude peak. And here we have experiments from bulk, iron, selenium, and some thick films, which are very similar at low energy, and they differ a little bit, still maintaining some main features in energy at higher energies. And you see the renormalized PBA is really off. The slave spins on PBA are still pretty off, and slave spins with on top of hybrid functionals give a very nice agreement both of the features in energy and the overall magnitude of the spectrum. And we pushed it a little bit even too far, and we investigated the Seebeck coefficient, which as a first approximation can be calculated without taking into account relaxation time. Indeed, at least we saw that the other approximations give a completely wrong sign and behavior of the Seebeck coefficient, whereas at least our formulation gives a nice agreement and also a change of sign, more or less, in the temperature, which is comparable to what you find in experiments, even if probably, this is a super sensitive technique, and the fact that we, for instance, we don't include spin orbit coupling, it's of importance, since indeed by including ex post some on our renormalized band structure, some spin orbit coupling, we find that it can be tuned to agree a little better. So this, I will take it as a very general, not so specific prediction, but at least much better than the other approximations. So let me just show you something about the many body physics, which I think it's very important, and which can be related to what we have just seen by the fact that we pretty stably, whatever the approximation we use, we place our compound in this zone just after the crossover into the Hund's metal. So we are close to the crossover, and indeed you can imagine that by applying pressure, you reduce the correlation strength compared to the hoppings, because you push the atoms closer to one another, and so you can get closer to this crossover. And indeed, there is one thing that I didn't mention. We always find where this crossover is positioned in all our simulation, a peak in the compressibility, in the electronic compressibility, which can be very important in screening, for instance, and in the even influencing the pairing mechanism, whatever the pairing mechanism might be. So it's the work of Pablo to show that if you put pressure on iron selenium, you can really bring the peak at realistic pressures at the realistic value of the interaction strength. Okay, so what I mean is that the compound is deep into the Hund's metal phase, and pressure brings it towards the crossover. And this is a nice agreement with the fact that under pressure the TC goes up. And Pablo has found this is in general the heat map of the compressibility, where you see you have a peak coming from a divergence that we find in all these calculations, even in models. So it's really something that I could explain. We have done a lot of work, but it can be explained, I mean, in such a short time. But it's really a feature of the many-body physics in these Hund's metals. This is the frontier is characterized by an increased compressibility, and if you move in doping towards alphaline, can even be a divergence. And the fact that you apply pressure, you bring the realistic, so this mustache towards the realistic values of the interactions, which are estimated, for instance, by CRPA. So this is what Pablo showed, the fact that when you apply pressure on and recalculate the DFT and keep the interaction, the interaction values constant and recalculate this compressibility with Slay spins, indeed you bring the mustache, this mustache of this peak of compressibility at the realistic values where the compound is. So basically, you can imagine that this enhancement of TC might be related to the increase of electronic compressibility. And this we see also in the comparison between bulk and monolayer. Yes, Chimiao?
It's already 25 minutes. Okay.
Okay, so I'm at the conclusions. So this is the last slide to show that we could discuss the same thing on the 111 family, and Pablo has calculated that also the TC in these families go nicely in agreement with the position of the peak and the Hund's metal crossover. And so let me just jump to the conclusions. I hope I could show you that we have improved agreement with experiments on the band structure of iron selenium, including correlations and using hybrid functionals, which includes screen toxic exchange, which is treated inaccurately by standard DFT. So this is needed, and that we can match several experiments nicely. And the important point is having this improved description from DFT and being in the Hund's metal zone. Otherwise, the bands wouldn't match at all. And there is an importance in being closer or further from this Hund's metal frontier, and maybe the fact that most of the compounds that we find with high TC are at or close to the Hund's metal frontier might be an indication that this frontier and the compressibility peak that you find there is a booster for superconductivity. So thank you for your attention.
Thank you, Luca. Yeah. Yeah. So question. Oh, so maybe we'll Ilya first.
Oh yes, okay. Luca, thanks very much for the nice talk. I have a question regarding the iron selenium. So I understood that when you compare, you always do the calculation for the tetragonal state. Yet very often when one compares with experiment, you look at the orthorhombic state. So I was just wondering whether, in your framework, is it possible, to do this DMFT calculation by assuming that you are in the orthorhombic ground state, and maybe even, put pneumaticity by hand and then see what's actually happening with the correlation in this pipe? Because what I noticed is that you still see 2 electron pockets at the endpoint in the tetragonal phase, and this is, I think, what is also experimentally seen. But we know that once we go into the orthorhombic state, there is this one pocket is essentially missing, and there is still a discussion whether it's basically because of the strong correlation, strong Z factor, whether it's maybe another effect of the nematicity. Could you maybe comment on this?
Yeah, sure. So indeed, we stuck to the tetragonal phase because the mechanism for nematicity is still subject to some debate. So it could be put by hand, but at the moment we don't have the possibility of having it spontaneously. So of course we could. Obviously, it doesn't make sense simply taking the orthorhombic Hamiltonian, because that has just a slight difference in the XZ/YZ due to the structural part. So we really need the feedback of the fact that nematicity is indeed a broken symmetry phase of electronic origin, and we don't have the mechanism for that arising spontaneously in our solution. So we could put it by hand, but then this would be subject to some other arbitrariness, because we would have then a driving field for this, and of course we didn't do it, but in principle we could.
Oh, Chimel? Yeah, I'm sorry, I'm muted.
I think Ming was Ming was.
Oh, Ming was first. Okay, Ming go. Yeah.
Thank you. Luca, thank you very much for this talk. I have two small questions. So one is that in your calculation where in iron selenium you're bringing down the XY whole band, does that change the filling of the XY orbital in this process? Or I don't know if that's even a relevant question to ask, bringing it closer to.
Well, it's not really a process, is what we find. And so you're asking me if in the end, the XY orbital is more or less populated than in the case of PB. I would say it's a little more populated, so it's a little further away from half filling compared to the PB. But I'm not sure this. I mean, this is just an outcome of the calculation. I couldn't really relate to anything in particular. Maybe also, this depends on the interaction strength. So what we checked is that our results are very stable when you move the U and the J in the range of realistic values, as long as you are in the Hund's metal phase. Now the specific value of the population of the XY orbital might differ depending on how you move U and J, but in general, it's very comparable between the two cases. I would say slightly more populated in the HSC than the PB, but not the inverse. That's for sure.
I see. And if I can, thank you. So the second question is, in your comparison of the DMFT calculation and the Say boson calculation, where you're saying they're very consistent. So I just wonder, from an experimental perspective, how do we distinguish the two in the limit where the Z is very small in the DMFT, whereas in the Say boson is 0? So I don't know if there's a way to experimentally distinguish the two cases in that regime.
So what do you mean the two cases? What you mean is that in some cases, one technique gives you 0 and the other gives you a small z. That's what you're saying?
Yeah. So you had this slide where for the DMFT calculation, it goes down and it has a tail that goes on forever. And then there's the Say boson calculation that just goes to 0. So
well, no, I wouldn't say that's general. That might be a specific case. Maybe I showed in. Okay, let me try to share again, so you tell me which slide you're referring to. But in general, I wouldn't say that this is a difference. This is a difference between these two techniques. It really depends on the calculation. It depends if you have finite temperature too, because it's my understanding that the Z equals 0 in these calculations can happen earlier if you raise the temperature, obviously, when you have a very small quasi-particle coherence. So in these calculations, so you're referring to this slide, right?
Yeah. So
okay. So I have to say two things. First, this is a comparison between the two techniques in the 3-orbital case. It's well known that, I mean, it should be clear, DMFT is more accurate in general. DMFT, it's slave spins, it's a cheaper, more simple approximation, which, however, gets more and more accurate with raising number of orbitals. So even if it gets also more computationally expensive, but this is also the case of the MFT. So in this 3-orbital comparison, you still see some differences in the curves, which are, let's say, the same color by color. But you shouldn't. These are just quantitative differences. Qualitatively, they do the same thing. So this doesn't go on forever. This vanishes here, whereas this vanishes here. It's just a quantitative difference, which is more enhanced in this 3-orbital case. In the 5-orbital case, it would be closer. But again, in general, the MFT it's a heavier but more accurate technique overall. So, but I never found a qualitative difference of importance.
Okay, thank you.
It's well.
Yeah, Luca. So nice talk. My question is connected to what I was referring to earlier, but also connected to Ming's question. Would you refer to this frontier? I think it's the same thing as what I was referring to, the precursor to the orbital selective mode exerting phase. And so I think Ron and I actually found that region first. And when we found it, we were looking for this sort of Holmes-driven versus Hubbard plus Holmes cooperating effect. And in our mind, the distinction between the two scenarios is whether there's a lower Hubbard bands and the upper Hubbard bands. If there is no lower and upper Hubbard bands, then charge is entirely coherent, spin may be incoherent. If there is lower and upper Hubbard bands, it means charge is as incoherent and localizing as spin is. And we always found that the lower Hubbard band, upper Hubbard bands exist. And by now, I think at least in Ming's data of FETSE, that's checked between theory and experiment. But my understanding that in FESE, that's also found by ARCA. So to me, U and J Holmes are cooperating, and the lower Hubbard band is really very important, especially in terms of enforcing whether the XY orbital is close to half filling, closer to half filling to be strongly correlated. Because if you want get a mass enhancement, you have to move it closer, the entire filling to be closer to half filling. And the low Hubbard band is a very important feature for counting the filling. So I guess that's sort of overall comment. I don't know whether you agree or disagree, but the question to you
well,
is...
I agree on one point, which is important. I agree that there is some confusion on what we mean by Hund's method. That's why every time I give a talk, I try to say exactly what I mean. Probably we mean the same thing, and I think that it's not really possible to talk about effects of Hund's coupling without acknowledging that Hund's coupling is always a fraction of the Coulomb interaction. So I think U and J always are important together. We are highlighting what happens due to J in the sense that it's the value of J, it's tunes things in a very sensitive way. But it doesn't make sense of talking about J without talking about U. So I agree with you. It's just in this respect, I think we are talking about the same feature, this frontier, which is the onset of selectivity. Now, I think it becomes from a sharp frontier, it becomes a crossover, just because when you include all the off-diagonal hoppings that you have in a realistic Hamiltonian, you simply can't have a sharp transition, so you always have some residual coherence.
Yeah. So, but let me actually put a question to you. So I was a bit surprised when you said that the correlation is moving the XY of filling to be further away from half filling, because we always found the opposite.
Yeah, in fact, in our HSE calculation, it's slightly less correlated. So I think this is some mechanism that we stressed a lot and we isolated in these very first papers that we called orbital decoupling. So it looks that in this zone, once you have activated the selectivity, the main trigger of correlation is the proximity of the orbital to half filling. So one has to know what is the population of the orbital, and typically the hierarchy in the correlation strength goes exactly with the distance of each orbital from its own individual half filling. And that's why when Ming asked me, what do I find? Well, I was just quoting the fact, I don't know if here I have the data, that the XY orbital that we find running slave spin on top of the standard DFT is a little more correlated than what we find when we run it on top of the new HSE. Of course, this depends always on the value. We could go to a much higher value of U and find a much smaller value of the correlation strength. But overall, where we deem realistic, we find a little decorrelation of the XY compared to our standard calculation. But again, the important thing is what is the value of the Fermi velocity that you find in the end. And this
we should probably move on, but
yeah,
just
let's move on. Yeah,
just text 10 seconds. Do you find the low Hubbard band because ARPAS did, right? So the spectrum.
I think, okay, in slave spins, as you know, it's not immediate to get the spectral functions, but indeed we have I mean, you showed it nicely in your papers. There is a way to calculate the Green's function and show that there are features which are unfortunately very peaked. But in DMFT, we do find Hubbard bands. Yes.
Mm-hmm. Okay, thank you.
yes. Thank you, Luca.
Thank you.
So can you unshare and then get Brian?
Yeah,
yeah, thank you, Brian. Thank you for your patience, Brian.
Sorry, Brian, for going over time.
No problem, no problem.
Okay,
I will show you how to
Brian,
go much more over time.
Great,
okay,
that's great, Brian. You can go, yeah.
You see the slides and the mouse?
Yeah, very nice.
Okay, great. All right, so thank you, organizers, for the invitation. And thanks for everyone out there listening. I will give a talk about related issues, iron, selenium, strong band renormalization, and in a nutshell, the talk will really be about how do we get from this picture to this picture. And the focus will be on non-local effects. So this is work done in collaboration mainly with these guys. And I will discuss several projects, but also there have been a number or a large number of nice discussions with these people here. Here's an outline. I will start with a short introduction, just sort of motivating the talk. It's based on the main puzzles currently existing for iron selenium. Then I will move on to discuss the issue of band renormalization, a particular kind of band renormalization, and show that it doesn't work for iron selenium. And then I move to the main part of the talk, which is a possible microscopic origin of this red-blue shift, the small pockets. And then I move into the low temperature phase and discuss the origin of this missing Y pocket. And to get this, we need to study pneumaticity. And I will show how intra-orbital pneumaticity might be important to this material. I hope time allows, but then we'll get to some orbital selective superconductivity here in the end. There are 3 papers that are relevant for this talk are listed here in black. And background material, well, there are many other talks in this conference series. We just heard Lucas, so there's a lot of background material there, but also we wrote this recent review paper, which is on iron selenium and its close cousins. Okay, so we're fascinated by iron selenium because it's a very flexible material. You can tune TC and the system goes superconducting from this pneumatic phase. We still don't know what is actually the detailed nature of this pneumatic phase. Another fascinating aspect that has been known for a while and which is a topic of a lot of research is what is the origin of this very, very strong band renormalization. What comes out of DFT? DFT is not just DFT, as Luca has just told us. There are many different versions of it, but the standard one that's in the literature is way too large pockets, also too large number of pockets, and strong ionization to what's measured in the actual low temperature pneumatic phase. Recent work by some of the organizers of this conference series has also shown that actually, there is a large pneumatic splitting, so a large difference in the RPS spectra if you go this way or this way, but actually there's a gap opening up out around the Y point, deep in the pneumatic state, which opens a gap and maybe even lifts this pocket above the firm surface. This is what we refer to as the no Y pocket or the missing Y pocket. The pneumatic energy scale is large, so it's of order, let's say 50 millivolts. And since these pockets, the Fermi energies are even smaller of that size too, it's not really possible to discuss the very low temperature band structure, low energy band structure on the Fermi surface without talking also about pneumaticity. So in that sense, strong band renormalization and pneumaticity are intertwined to get to the final low temperature band structure and Fermi surface. Okay, so this is in a nutshell the question, as I said, how do we get from here to here? And to answer this question, I will address the questions of strong band renormalization and the nature of the pneumatic state. Of course, we're not the first to address this at all. This is by far not a complete list. Here's the paper that Luca was discussing. For more details of various techniques and so on, I can refer you now to Luca's presentation, but also some of the review papers here. Lots and lots of works. Since the very beginning of these materials have been dedicated to obtaining better models that incorporates strong correlations and the feedback on the band structure. But what I'll focus on is a particular couple of versions of that, as we'll see in a little bit. The second part of the second large motivating aspect of studying this material is this very unusual superconducting gap structure. So the pockets are very, very small. This is the whole pocket, and here's the electron pocket. But even though they're so small, the gap anisotropy is very large around these very small pockets. That's very strange, and we've been fascinated for a while about how do we explain this gap structure. And there are some new developments coming about because there is apparently no electron pocket there. So the picture is changing a little bit. But more generally, there's of course the current very fascinating question of what is actually the nature of the superconducting state that emerges out of such a correlated metal. Could be a Hund's metal, being a pneumatic Hund's metal. I think that's an unsolved question. Okay, so let me go to the second little part of this presentation. So there was many, as I said, many proposals for band renormalization in these multi-band systems. One of the ones I want to bring attention to is an early one by Hortensi et al. Where they just pointed out that if you have some mode coupling between hole and electron bands, it quite naturally will lead to a pocket shrinking. Okay? But since we have so many more experimental details nowadays, it's worth revisiting this mechanism, not in toy models, but actually in sort of more material-specific way, and see quantitatively how much of this effect is actually out there. So we tried to just revisit this by including realistic band structures, correlations, and then calculate the self-energy in one-shot calculation by including these kind of diagrams, typically relevant if you have strong spin fluctuations. And this is not the main part of my talk. I'll just show you the results of doing such a calculation for 1111, LiFAS, and Selenium is that, yes, there is such a pocket shrinking. The mechanism is there. You can compare the bare bands and the renormalized ones in yellow. This is just the spectral function calculated here. So there's a generally a shrinking, but the whole point of what I'm saying is that for iron selenium, this doesn't work. This mechanism is not capable, as far as we can see, at all of getting the right pockets, the number of the pockets and the size of the pockets. So what has been known then for a while also, started as far as I know from this paper, is that non-local correlations do this quite naturally. So, for example, if you just include nearest neighbor Coulomb repulsion, we focus on this side first, mean field decoupling immediately leads to pocket shrinking, and I will go through this in actually quite great detail in a few slides from now. How does this happen? But just straightforwardly, you get very small pockets, and you get these kind of propellers for Selenium doing the same thing for LIFAS generates. This is not a generic result. It depends very much, of course, on the starting band structure. And now, of course, we start entering discussion of whether these longer range Coulomb repulsions are really larger in this material in Selenium than other materials. One might speculate that spacing layers leads to less screening and so on. I think this is unknown, but there are actually some calculations, CRP calculations pointing to that effect. Oh yeah, and this was just to point out that we used this mechanism from ab initio, we calculated the pressure dependence of these interaction parameters to try to come up with a possible explanation for this phase diagram of how conductivity, superconductivity, and magnetism changes with pressure. Side remark. Okay, let me get to the main part of my presentation. And so now we will just focus on what are the effects of longer range Coulomb interaction on band structure. Okay, there are obviously very strong band squeezing, strong coupling effects from Kunz coupling and U prime. But for now, I will ignore them and just see what is it that the nearest neighbor Coulomb repulsion does. So we start from a realistic band structure, an iron selenium, and we add this coupling. There will also be spin-orbital coupling. And for this particular talk, I will only include the LSET. Now, iron selenium is a material that belongs in the space group of P4NMN. That is a non-symmetric space group. So some of these the elements, symmetry elements, include small translation, and the real physical unit cell is actually 2-ion unit cell. However, for convenience, it's often much easier, at least calculation-wise, to address the problem in the 1-ion unit cell. Doing that, the right factor group is lowered to the subgroup, and this correct subgroup is actually D2D, not D48, it's D2D, because the right sort of downfolded band structure knows about the arsenic being above and below the planes. So the group elements are some 180-degree rotations and mirror, and then it's not a C4 rotation that's in this element, it's S4. Okay, so the Hamiltonian of the 1-ion unit cell is only invariant under these symmetry operations. So if we discuss and study the effects of pneumaticity arising from nearest neighbor Coulomb, it really means breaking of S4 symmetry. Anyway, that's a bit technical, but not extremely important. I will now start with this band structure that was generated for iron selenium in this old paper, and then we will simply check what are the effects of nearest neighbor Coulomb, both in generating band renormalization and pneumaticity. Okay, this is the most technical slide. I apologize, but we have to go through a few things in order to understand the results that come out of it. It's not complicated. We just simply take the nearest neighbor Coulomb, define, we mean field decouple it. So here are my mean fields, and this is straight on the mean field. And I have a form factor, which for nearest neighbor is just cosine kx plus cosine ky. Now, in line with what was done previously, it's convenient to define a symmetrized version of this field. So this is just an averaged field over these S4. You can think of these as C4 rotations. This is the matrix representation in orbital space of S4, and simply average over them. So this is explicitly symmetric mean field quantity. And the rest is just going to be a symmetry breaking point. This will not exhibit that. Now, I will additionally write these fields in these basis functions of D2D, and these will just be formed factors like this. So Fs looks like this, and Fd is of this form. Okay, so the final mean field Hamiltonian resulting from decoupling just the nearest neighbor Coulomb has this form in terms of these two fields. You'll notice there's an alpha in here. I will allow myself to play with alpha. And the philosophy behind that is the same as in the earlier works, that these are belong to different symmetry classes. So in an RG sense, they might flow differently. And so even though strictly speaking, the bare decoupling alpha should be 1, we will allow it to be different from 1. Other than that, we just run code, start with the 5-band model, and unrestricted and calculate these mean fields. And here are the results. So this is just focus first on the bandwidth normalizing part. This is a matrix in the S-wave channel and here in the D channel. Okay, so this shows you which orbital components contribute to these mean fields. And the first part to notice is the diagonal elements in the S channel, and over here we have also some structure. So let's see what this does to the bare band structure. Focusing first on the S components, you see that the dx set and dy set will be renormalized down. So this means the whole pockets at the gamma point will be renormalized down. It shrinks the whole pockets, the gamma point. However, the opposite sign in the xy orbital here, you might think this is almost up, but the form factor changes sign out at pi. So that's actually also renormalized down. So this is exactly why the pockets shrink in this case. In the D-wave case, in this particular channel, we have the opposite sign at the x and the y point, but the form factor also changes sign exactly at those points. So the electron pockets are shifted up. Okay, so this was known. Just spending a little bit of time explaining why do pockets shrink arising from nearest neighbor Coulomb. This effect we immediately get. Now, if you ask me why these results come about here, I can't tell you that. That is a feature of these models. This is not particular, and this is sort of generic. It's not that we change parameters and we get completely other elements. It's the numbers that change, but not the structure of this. Okay, by the way, this is exactly why you get peanuts. It's related to this factor here, because if you're shifting up only, say, the green part or the red part of these pockets, then you're squeezing only along the side, and that's why you immediately get a peanut-shaped electron pockets. Okay, going to further, or looking now in the symmetry breaking channel, there is no S component, but there is a D component. And there's a lot of structure here. So this is nematicity arising from nearest neighbor Coulomb in a realistic 5-orbital model. It's in the D channel here. And what you see is, first of all, there's an asymmetry now. These have the opposite, the same sign, but the form factor is then giving them a sign change. So there's a small shifting up and down of the electron pockets arising from nematicity. However, the largest component is this intra-orbital component connecting xz and xy. Okay? There will be another domain where it's xz and yz. But this is exactly what causes this, or what leads to this gap out here. So that it hybridizes these two bands, and if this is large enough, it can actually lift this pocket above this. But quite generically, this intra-orbital component is the largest component that we find. So that's why even if you start, that's why you can end up with this kind of band structure with smaller pockets and a gap at one of them. And that's how you, from purely nearest neighbor Coulomb repulsion, quite easily get a scenario where starting DFT's band structure has changed into something that looks quite like what's seen in iron selenium. At this point, I should refer you to a number of other papers. For example, the fact that there's intra-orbital DXY nematicity. This has been discussed quite a bit recently in these works. And also, there's another mechanism for obtaining this missing or no Y pocket scenario actually coming from that component, as you can see in this paper by Eli Yerman and Luke Rhodes and collaborators. And by the way, in this paper, it's also nicely, there's a nice discussion of connection to other experiments, how to explain quantum oscillations, and so on and so forth. So it seems to me that this is qualitatively in agreement with the recent developments of ARPAS, that there's a missing electron pocket, that they have this peanut-shaped pocket here and only a small hole pocket around the gamma point. We can discuss the quantitative aspects, of course, like how big are these gaps and how big are the numbers that you need to put in here. In my opinion, that is a discussion that doesn't really make a lot of sense at this point, because we did not include initial squeezing from U and J. All these numbers will depend on the initial band structure. And as was explained in earlier talks, this initial dispersion is way too large. Okay, so all these effects should be built on top of probably a much renormalized band already from U and J. But what I do want to say is that the sort of symmetry analysis I did of my mean fields is not really a proper one. What I did a rotated, a sort of symmetrized one, and then a non, then the rest. Well, what is the rest really? So what we should really do is we should just take our calculated mean fields and decouple them in these irreducible representations that's allowed in D2D. Right? Well, we did that too. And as we cool down, we see something interesting. There's actually two transitions happening here. First, this transition into the B1G channel. And at a lower temperature, there's a transition into this, we call it the EX channel. So it's a part of this two-dimensional representation. One of the components gets condensed and breaks this here. So now there's a number of red alarm bells and open questions coming up. Before we discuss that, I will point out a very recent work. This is a DFT work, also with hybrid functional, as far as I know, where they actually find also point out the fact that there is only one electron pocket coming out of intra-orbital nematicity, but I believe their structure is different from ours. I don't know exactly where theirs comes from in great detail, but sort of superficially, it's very similar. It's a condensed nematic intra-orbital component in this in two-dimensional representation. Now, of course, if you have this, there are a number of issues. You should see a double transition, which I don't think is seen. Then, of course, they could be accidentally close to each other, or they might couple weakly to the lattice or to probes. That's one thing. Personally, I think more that what we have learned and what might be relevant here is that the iron selenium is very soft, and it's full of these microstructure components. This was studied in some recent works, and it's only the average compound that looks orthorhombic. So it could be that at a local scale, you have these components. Maybe you have them because you do have several nematic components that compete with each other. I don't know. This is an open question, but I think it's interesting to pursue, and we should think more about how to use this to understand material or rule out this scenario. Okay. What is the consequences for missing Y pocket on the spin fluctuations? Well, if you just do the RPA calculation with this new band structure of Fermi structures with no Y pocket, you get the wrong signal. You cannot explain the pinching dies, highly anisotropic spin fluctuations. Actually, the dominant scattering is still pi, and there's hardly any symmetry. Actually, this one is a little larger. It's supposed to be this one. So you can solve this, or you can cure this problem by including quasi-particle weight factors. This is something we have discussed a lot previously. You can also probably cure this. This is something that was discussed briefly with Eli Yerman. You can probably also discuss this by some general background of inelastic scattering. I mean, the reason you get such strong pi-pi scattering, even though there's nothing pi-pi, you would think that you would get a large peak in the spin susceptibility just from this vector here. But it's not the case in these systems where there's large contribution from higher energy processes. But if they are washed away by some self-energy effect, you might get back to a picture where this is strongly enhanced. Of course, in reality, you will have momentum and energy-dependent self-energy effects. So all the physics will be in there. There will be some what's quote orbital selectiveness, and there will be also general effects of weakening from general inelastic processes. In terms of the superconductivity, things have changed a bit. Like, all that matters, if there really is no white pocket, is the Fermi surface itself. And whether you do a plain vanilla spin fluctuation calculation just with this band structure, or whether one includes suppressed quasi-pilot wakes in the XY channel, or splitting because of pneumaticity in the X and Y set, but these effects should be there in the real material. You calculate them, they are there. But whether you include them or not in the calculation of superconductivity is irrelevant. This is something that was also pointed out in this paper here. Okay, so that concludes my story of iron selenium for now. I will just, in the last few minutes, I hope I have a few more minutes, nobody's complaining too much. I will show you a scenario where orbital selectivity or band or orbital dependence is very strong on superconductivity, and it's opposite of what might expect. And I think this is interesting because it relates to the general questions of whether interactions are friend or foe of superconductivity. Typically, we would say you need interactions to generate unconventional superconductivity. And the more you have, the better, unless you start going into a mud regime or so on. But in this metallic systems, where we have multi-orbitals that are relevant to Fermi surface, there's another question, which is, if you have these kind of iron-based systems, where will the superconducting gap actually be largest? Now, I'm not talking about Fermi surface effect, Fermi velocity effects, the density of states and so on, but just in terms of interactions. Will the superconducting gap be largest or smallest on the most correlated orbital? Naively, one might say it should be largest on the most correlated orbital because that has largest U or J. However, that turns out not to always be true. And so that's a very complicated question. And, this is the heart of a lot of research these days, trying to capture in some unbiased way the origin of superconductivity in correlated multi-orbital systems. It's not a solved problem. But what we can do is that we can run the flex. So flex is a way to do, because to answer that question, we have to do some self-consistent calculation. We can't put in self-energy effects by hand, and then we get what we put in a sense. So we have to do some self-consistent calculation. So I won't explain flex, but it's an old technique. You're running, basically finding the correlated Green's function in terms of certain number of diagrams, and it's the same diagrams that enter into the self-energy and into the spin susceptibility, and therefore you can feed that also into the pairing kernel in the end of the calculation. So we do that. Again, we find pocket shrinking. This is the same as this, basically the same as this Hortense mechanism. The Fermi surfaces change a little bit, but the main part of this whole exercise, and this is the main part of this paper we wrote here, is that as your bare Fermi surface, you will have you might have such a scenario here. This is typically what you have. Now, I'm by the way using life as an example because it's simpler. I don't have to worry about pneumaticity and so on. And so often what happens is that the XY orbitals are dominating one, largest Fermi surfaces or largest density of states. We have the largest peak at pi0. This is just one intra-orbital component. It's calculated by Andreas Kreisel, and you see that the XY orbital is large. This was, in fact, the original problem of iron selenide, getting gap structure right to get rid of this, and to invoke very strong quasi-particle weight reductions to get rid of this. Now, what happens if you run the flex is quite striking. They are inverted. So now in the new renormalized susceptibility, it's actually the X in this particular direction is X set susceptibility that peaks over the XY. The reason for that is it's the same virtual processes that enter into these the susceptibility and the self-energy. There's a large susceptibility means a large self-energy. So you have to find the balance, right? So the self-energy will smear out this blue peak, it'll lower it. And the question is, how low does it go? And it can actually be such that it's inverted. And this is exactly the picture that one gets in the sort of poor man's version, trying to include self-energy effects in superconductivity by incorporating quasi-particle weight factors. So in fact, if we could be putting in this generated pairing kernel into the linearized gap equation. This is what Andreas did, and then he plots the gap. This is when here the Fermi surface looks like this. Hole pockets in here, and hole pockets are here, and then two large electron pockets. It's an SY superconducting gap structure. There's a sign change between the hole and the electron pockets. But what you see if you run the FEX is that the XY contribution is substantially decreased. So everything that was XY on the Fermi surface, that's in the tips of these pockets, and this whole pocket is fully XY. Here the gap is basically washed away. Okay, and exactly the same you get if you calculate the quasi-particle weight factors and just put them in, sort of in a poor man's version at the RPA level, you get almost exactly the same gap structure. So this is a nice example, in my opinion, of how do these sort of orbital dependent interactions affect superconductivity. And it's an example of most correlated orbitals being harmful to superconductivity, which was in this picture of orbital selectivity. Large or small set factor means small gap if you just put them in. Here's an example of how that comes about. Of course, it will be very, very nice, and in future studies will for sure correct some of the problems that is in this flex approach, and hopefully, or maybe we'll see that this holds true for more rigorous methods. Okay, I am at the conclusion slide. So I have shown just briefly how longer-range Coulomb repulsion naturally can lead to these red-blue shifts, small pockets. There's an interesting inter-orbital large pneumaticity component that is sort of microscopically generated also from the same mechanism. It might be the explanation of the no Y pocket in iron selenide. And then I showed you an example of a self-consistent calculation with susceptibility, self-energies, and pairing, where there was this orbital inversion, which strongly affects the gaps. And if this holds true, I think this is a very important mechanism to keep in mind when we're trying to explain gap details. When we're trying to, we get an ARPAS experiment and we see gap wobbling around certain hole and electron pockets, that might not just come straight out of a bare calculation. If one has to include such self-energy effects, they might even be explanation for some of these strong anisotropies around pockets. Okay, I think that's it. I will stop here.
Thanks a lot, Brian. Yeah, it's a very interesting talk. Yeah. Okay. So I'll try to ask you a question first. So which orbital then do you believe is more important for superconductivity? I mean, you said XY may not be so important, right? But what is between YZ and XZ? Do you have a feeling which one?
Which material are we now?
Oh, yeah, I mean, that's general, just in general, right? I mean, yeah.
Oh, general. Well, it's hard to say. I mean, if you take a general multi-orbital system, here you need interactions to get unconventional superconductivity, right? But what is shown here is that there can be cases where what you might think should be the strongest, or what is the strongest correlated orbital, you might guess maybe would have the largest gap, but that is not the case. There's some complicated compromise. So I don't know. This depends on how big this effect is.
What about for iron selenide?
Well, for iron selenide,
it's a DYZ, right? Yeah.
Yeah, it's a Y symbol. Yeah.
But what about the cobalt barium 122?
Don't know.
Okay. Any other questions? Oh, okay, Ilya.
Hey, Brian, thanks very much for the nice talk. I have a question on the following issue. So I understand that, if I start in a single band model and I include the longer range Coulomb repulsion, usually my understanding is that it tends to suppress spin fluctuation. Okay, so now, of course, in the multi-orbital case, the situation is much more complicated. And but now I understand in the scenario for the iron selenium, you need a sizable interorbital pneumaticity induced by this longer range Coulomb. So it essentially needs to be one of the significant interactions. Now, if you go to the the question is, did you compute the spin susceptibility by including also the next nearest neighbor Coulomb repulsion? Because I understood you discussed the effect of the Fermi surface topology change on the spin susceptibility, but do you know what would be if you now also include this longer range Coulomb in this RPA loop, let's say, and see whether it will suppress spin fluctuation or not? Because, experimentally, we know that in iron selenium, in the nematic phase, the spin fluctuation are there.
Yeah. No, so good question. No, we didn't do that. We could do it actually. Include. I mean, this is just a standard calculation for where longer range Coulomb was not included specifically in that was your main question. Yeah. You're right that generally nearest neighbor Coulomb will boost charge susceptibilities, and then there will be some kind of competition between those two. Yeah, but then it just boils down to a matter of parameters. How big is U compared to V, and so on. So yeah, we could look into that, but we didn't.
Any other question?
Maybe since nobody else is asking us, can I ask a question, Pencha?
Yeah, please.
Just sort of step back, Brian, just to take advantage of this setting and ask your opinion. So FESE, the pneumaticity in many ways is different from 122 necktides, and FETE is different, etc. So there's a lot of variation across different materials. Do you think that combining this nearest neighbor Coulomb repulsion or just longer range density interactions, along with the outside U, homes, etc., do you feel the prospect of getting overall picture of the variations across the materials as far as pneumaticity is concerned, or do you think that it's still early stage that we need more information?
Yeah, difficult question. It's an interesting thing to. I don't know, but I was surprised of we don't know that much about pneumaticity in some of the other materials, right? Because magnetism sets in. I mean, it's just purely experimental.
Mm-hmm.
So we want to access the low temperature property of these phases. I mean, there are some recent developments, forget the exact references now, of this momentum-dependent pneumaticity also in some of the other materials.
Mm-hmm.
And so certainly the original picture that many of us used of just some ferro-orbital splitting turned out to be way too simplistic. I don't know if nearest neighbor Coulomb is the answer to all this. I doubt it, because there's plenty of other ways to generate pneumaticity in these systems. I just find it striking how simple it is to get the right bands of iron selenide using this mechanism. And again, we're not the first to point this out. This was pointed out by others already, but we revisited it and found some interesting things in terms of this interorbital pneumaticity.
Fair enough. I mean, there could be other mechanism underlying, but Coulomb interaction, the further neighbor interactions or longer range interaction would be part of the story in affecting the underlying electronic structure, I suppose.
If I may, I think that it's not just an added element, because it's really something which is known even in realistic simulations is the main thing which is left out. So in practice, we with Brian, we have done very similar things. Okay, our use of hybrid functionals is basically integrating in the DFT exactly the short range Fock exchange. So it's nearest neighbor. It's the first. It's not really long range. I mean, in this sense, is the first contribution beyond the local interaction, and that is known to be needed to correct the self interaction error of DFT. So it's naturally the thing you want to add on top of a realistic Hamiltonian coming from DFT. So in this sense, I think it's a mechanism that simply by the fact that it's one very important missing piece to any realistic band structure, it's probably the first thing that should act to induce the shrinking or the nematicity. So I think there's good chances that this is one of the main pieces missing.
I mean, I think it's fair. It's just a question, are we at the stage after 10 years, are we at the stage of getting overall understanding of the variations of nematicity vis-a-vis magnetism and other things across these different materials? And I think, you know, it seems like an interesting ingredient. I don't know in the end whether it's going to be playing an important role or not. And certainly it would be good to explore.
Okay.
Yes.
Okay. If there's no more questions, let's thank Brian and Luca again. Yeah.
Thank you both.
Yeah. Thank you. Thank you. Thank you very much for giving these talks.